So although we delved into derivation with the limit on both sides, we had h to the left and h to the right, we didn't actually ask about how it would be if these two sides are different. So we now know that derivatives can be taken in a central way with h to the left and also to the right. And let's extend this prompt and try to see if we can have different things on the left and the right and then find some expressions in terms of that, because that would be interesting. So, but what about derivating without limits and allowing a different distance to the left and to the right from the derivation point? Label these distances, how would we call them? A and B. So let's see what it does. Alright, generalized finite difference derivative. Limit as h goes to 0, you approximate derivative using 2 points at different distances on each side. Point of interest being x, and then we pick distance a is bigger than a or 0. Left point x minus a. Distance b to the right x plus b. Linear approximation to the derivative using 2 points. Okay, so we have a general asymmetric formula for this. So we would have slope of the line x minus a and f of x minus a. That's kind of what we wanted. And x plus b and f of x plus b. And they say approximate. Asymmetric finite difference. So there's a name they gave it. The chat here. Why this works? This comes from approximating the derivative using the secant line. Yes. But instead of symmetric spacing, you allow different distances. Then we can have a secant line. Look at a smooth function, like take example x squared or something, a very simple example. A is b is h, you recover the standard central difference. We did that before, but we now want the h to be h1, h2, different distances, not the same to both sides. So we don't have to take a limit, we can kind of do some accuracy inside. So we can do Taylor. We have Taylor expansion, f of x plus b and f of x minus a. Oh, so there's a lot of algebra now. So if they subtract things, and what does it give? Well, there's a lot of algebra, and then the key takeaway. So the formula is exact only if in the limit or when a is b. Well, let's actually delve a bit into this. So what about if we care the distance a and b to give us how far we have to be from the derivative point in order to have a parallel secant line? Because much deeper geometry question now, they say. Yeah. And now if they divide both sides by a plus b, the average slope across the interval x minus a, x plus b. So that's what it tells us here. Well, symmetric case, a is b. That's we had that, so that's not a new insight. What we want is this, yes. So example of a quadratic function. So in the case of x squared is b equals a. So let's see what happens for x cubed, or a deeper insight, okay. We can do a Taylor expansion. I'm not sure if this is correctly calculated, okay. This is what just it tells. But anyway, whatever it now said, let's care about what about x cubed and what is the relation between a, b, depending on whether a polynomial function is odd or even. That's useful. We have x cubed and the chat nicely just gives us all this calculation without effort. Oh, so we have some equation for b and a. So now we have this relation between b and a if we want the parallel secant line derivative here. And set equal to the derivative, yada yada yada. Okay. So we would have this. And then okay. So there's a condition, final condition for this function. And the b and a to the left and the right, so that they're a parallel secant line. Unlike the quadratic case, symmetry alone is not enough. If a is b, this becomes a squared is not 0. Okay. I'm not sure to which extent all this is accurate, but I would. Okay, so and then we have to solve explicitly for relation AB. Okay, so there's some further intuition. Even versus odd polynomials. So even functions favor a is b. Okay. I'm not sure if it's always. And odd functions are antisymmetric, introducing skew, they say. Taylor expansion has odd powers and don't cancel symmetrically. The residual error is left. And then we have a more complex expression for the relation between a and b. And there's a unifying idea. Secant slope, tangent slope. Curvature effects plus skew effects. So I don't know if there are some technicalities that we can go deeper with here. Okay. How would one deal with non-polynomial functions? And we'll wrap it up there, otherwise it's a big rabbit hole. So the general theory behind what you've been building. So for non-polynomial functions, nothing fundamentally breaks, but you lose the finite algebra closes nice. Instead, everything is governed by the function's Taylor expansion. It's local behavior through all derivatives. So you start from the same condition, alright. It will require yada yada yada. And use Taylor expansion. So we would keep using Taylor expansions. For the secant to be parallel to the tangent, all extra terms must cancel. What this means? For polynomials solvable exactly, for general functions, usually only approximate solutions. Well, I mean, this is just a rough, reaction. So that's, chat tells us all this. Yeah. So, okay, if we have e to the x, sine x, let's see what it does. So, for example, intuition, for f of x is e to x. All derivatives e to x, so the condition becomes this. No finite truncation solves it exactly, but small asymmetric AB can balance the series. Okay, let's please do a full solution. Please do a full solution for e to the x. We'll see what it does. Yeah, it's basically this expression, e to the x plus b minus e to the minus e to the x minus a over a plus b. And then you factor out e to the x. Ooh. And then you cancel e to the x. Okay, so then there's the relation between. Oh, so again, basically the full idea here, what we want, even more than getting the derivative, I guess, to get the relation between the a and b. Oh, and it doesn't depend on x. Alright. So I will wrap it up here. This is interesting. So if you want the parallel secant line for points on e to the x, then if this was calculated all correctly, here you have a expression. Yeah. So we'll wrap it up here.